Hi everyone, my name is Madeline Hart and this is my video lab report for Lab 1, Constant Velocity. In this lab, we use Python to construct a computational model that predicts the motion of an object moving at constant velocity with no external forces acting on the system. We compare the computer predictions with that of a real-world example, a rolling ball, and we set the computational model to have the same starting velocity as the velocity observed. This lab is important because it gives us a visual representation of Newton's second law of motion, which is the final velocity is equal to the net forces over mass times the change in time plus the initial velocity. But because there is no external force acting on the object in the computational model at least, the lab is also a good example of Newton's first law of motion. The ball should theoretically maintain a constant velocity throughout the simulation and observation. Inertia is an important factor in the behavior of the ball in the simulation and observation because the ball in motion continues in motion when no outside forces act on it. As you can see in this video, the velocity of my ball slightly slows down at the end as well as the ball moves away from the camera at the end of the video. My results show a small amount of deceleration in the observational portion, likely due to outside forces such as rolling friction or air resistance. As you can see in the video, the ball not only slows down at the end but also rolls away from the camera. I can improve my results next time by using a smoother ball and rolling it straighter. As you can see here, the straight slope of the position versus time graph of the computer model indicates a constant velocity, which is expected because there are no net forces acting on the object. Here's a video of my computational model on Python. This particular model was probably chosen for this experiment because we are able to program the ball to maintain the same velocity as the initial velocity as long as the forces acting on it are zero. So as you can see, the ball just rolled in a constant velocity, and the position versus time graph shows that this constant velocity is the same velocity as the initial velocity in my tracker video. As you can see here in this graph, the observed position versus time and the model position versus time begin with the same velocity shown in the beginning portions of the graph, but as time goes on, the observed position versus time graph slows down while the model position versus time remains constant. The what if question here asks what would happen if we switch the axis on tracker away from the axis that is parallel to the ball's motion. When the axis is switched, the data is much less uniform, as you can see here in this graph. For example, I switched the x and y axes, but the data still remained as an upward slope, but without the uniform line that it had previously. Before the switch, the position of the ball was almost entirely parallel to the x-axis, but when the x-axis is placed perpendicular to the motion of the ball moves much further away from the origin. Here, at the end of the trial, the ball is 4 meters away from the origin instead of the normal 0.8 meters. The what does it mean question asks if we can predict the forces that are acting on the object that all cancel out to zero. In my observational model, the forces do not cancel out to zero, but the forces in the positive x direction are zero as there are no forces propelling the ball forward, but there may be rolling friction and air resistance acting in the negative x direction against my ball. Can't necessarily predict all of the forces acting on the ball, especially in the observational model, but we know that since the ball maintains a constant velocity in the computational model, that all of the forces are either zero or they add up to zero and cancel each other out.